Okay, welcome everyone. Um, Today kita akan cover ensemble classifier. So for the past few weeks, you have looked into the classification tasks, which involve a few algorithms such as decision tree, nearest neighbor. What else? You use the bias classifier. Okay, so all those considered as individual classifier. So for this week, we will look into how we're going to combine the classifier and we form an ensemble classifier. Okay. Okay. As you know, each of the classifier that you have learned, they may not work in for a specific domain of dataset. So you may have to try a few individual classifier, and then you may choose the best classifier that have the highest accuracy. Okay? But there is another way on how you can combine all these classifier. So by combining them, you will get a better accuracy because some of the classifier um, may not give you a good result. So for that reason, um, in this section, we will look into how do we combine the classifier. Okay. So the basic idea of the ensemble is how do we combine a few classifier given the data set, and then how do we combine the result of all the multiple classifier that we use. So when we talk about ensembling, ensembling is a technique of combining two or more algorithm of similar or dissimilar type. So it could be the same classifier or it could be different classifier. Okay? So the way you combine them or the type of classifier that you combine will depends on the name of the um, ensemble. So in this session, we will look into three type of ensemble classifier. Okay, so by combining them, we will make a more robust system which incorporates the prediction from all the baseline, meaning that some classifier may have advantages, some may have disadvantages, but by combining them, basically we are trying to get a robust system which is very flexible in terms of performing the prediction. Okay. So if you look at the diagram here, this is our original data. So we split them into T partitions, okay, create multiple data sets, and then we will feed them into um, up to T classifier. So each of the classifier here will produce their own result, and then we collect all the result here, and then we form the final answer by combining them. Okay, so it depends on the answer that you get here. Um, if you use regression, of course, you will get numerical value. This is if you are performing regression. So when you perform a regression, you will get individual value here. So how do we combine them? We just take the average. Okay. But if you are getting categorical value or the label here. So we will use the voting method in which we get the most voted label. Okay. So we will look into that one later on. Okay. So for example, if we get all the result here for these three model, so we are using three classifier. So what we can do is we can take the average. Okay. So the average prediction will be computed based on these three results that we get from different classifier. So basically, we are using classifier 1, 2, and 3. Okay. If you are getting categorical or label as your output, so you may take the majority voting. Okay. So majority vote will be put here as the main class. So that's how we combine all these classifiers. Okay. But there are some method in which we use the weighted average, in which if we get the prediction 45, 40, and 60, so the total here is 1, so which means that we put which one is more important. So in this case, we are saying that, okay, for model number 1, we get 0.4, that is the weightage. And for model 2, the weightage is 0.3. The weightage for model 3 will be zero point 0.3. So if you compute this by multiplying this with the prediction, and then you add up all this number, you get 48. Okay, so this is the result that coming out at the end of your combined classifier here. Okay. So like I mentioned just now, there are three type of ensemble classification method. Okay, so namely the bagging, stacking, and boosting. So the name of your ensemble depends on how you arrange them, how you arrange the classifier, and how do you divide the data set and feed into the classifier. Okay, so looking at the first one, bagging. Bagging consists in fitting several base model on different bootstrap sample, meaning that you will get four different type of data set. So your initial data set will be divided into a few chunk. Okay, so they all different data set. Okay, so in here you will use the same classifier. Okay, so normally they call it weak learner. Weak learner meaning that they are performing not very good, but if we combine them, they become a very robust classifier. Okay, so this one we will have the same type, and then the result of each of these classifier will be combined. So it depends on the output that you get here. If you have numerical value, then you take the average. If you get the categorical value, then you take the majority vote. Okay. So this is bagging. So bagging consists of different partition of dataset and use the same classifier, the same model. Okay. Okay. The next one is boosting. Okay. So boosting we arrange the classifier in sequence. So for example, this is your dataset. Okay. For each of the learning process, they will use the same dataset. Okay. So we will use the same method here. Okay, so the same method. So every time when we perform or modeling the data here, so it will adjust the weightage of each of the individual record in which the correctly classified item will be less focused. Okay, we will focus less on those items. But item that was incorrectly classified, we will increase the weightage so that any adjustment will need to focus to the incorrect classified sample. For this session, we will look into this detail. Okay, so once we change the weightage here, then we use the same data again, but having different weightage, and then we will perform again the modeling here, and then the final model will be here. So the final model will basically combine all the knowledge that we get from the previous classifier. Okay, uh, they call it aggregating the classifier to become a single model. Okay, so every time the training data set is processed, they will be updated. Okay, but we are using the same classifier here. Okay, so the difference between the bagging and the boosting is that the bagging, they perform the operation in parallel, but in boosting they are perform in sequence. Okay, so we are using the same classifier, and the output of the previous classifier will be used for the input of the next classifier. Okay, we will go into this one in detail. So for this session, we will focus on this boosting. Okay, and the last one is stacking. Okay, for the stacking, we use the same data set, feed into the same, no, we could use the same model, or we could use different classifier. Okay, so over here, it could be homogeneous. Homogeneous means the same classifier, or non-homogeneous, which means it could be KNN combined with random forest, combined with uh, support vector machine, and many more. Okay? And the output here will be given, will be taken, and we will do the necessary uh, action, which is taking the average or taking the majority vote. Okay? So these two are easy to understand, but boosting is a bit different. So we will look into that one. Okay. So this is just to make a clarification the differences between the bagging, the boosting, and stacking. Okay. For the bagging, building multiple model same type. Okay, selalunya same type from different subsamples. So this is the uniqueness of bagging. So always remember that when we use bagging ensemble, basically we are using different subsample. We are um, dividing the main data into a few partition, and then each partition of data will be fed into the model, each model that we have in the ensemble, in the bagging ensemble classifier. Okay. Compared to boosting, we're building multiple model, each of which learn to fix the prediction error of a prior model in the chain, meaning that every time we finish modeling the data, it will focus on the error that we have. So all the incorrectly classified item will be focused more on there. So we put more weightage, and then the next model can focus on that one. Okay, so they are arranged in sequence. Okay, lastly, the stacking. We're building multiple model, um, typically of different types. Okay, so we are combining a few types. For example, KNN, super vector machine, decision tree, and many more bias classifier. Okay, and learn how to best combine the precision of primary model. So we could go for taking the average for the regression, or taking the majority voting. Okay, for the boosting, so we focus on the boosting now. So in boosting, after one classifier model the data, it will pass the data to the next classifier, but they will have different weightage of individual item that we have in the data set. Okay? So for each of the interaction, okay, we will focus more on the misclassified training document. This is when we are looking at how do we classify a document lah. So at each iteration, each document is trained in training set is given a weightage or a weight. Okay, so basically we start with if we have 10 item in our data set, so each of the item will have a weightage of 1 over 10. Okay, so if we have 100 item in our data set, so each of the item that we have will have 1 over 100 as the weightage. Okay, so the weightage of incorrectly classified document are increased at each round, meaning that when you perform the classification, all the misclassified will have higher weightage, and all those who are correctly classified will have um, lower weightage. Okay, so after n round, meaning that after you performing n number of classification, so the output of the trend classifier are combined in a weighted sum. Okay, we will look into this, and then weight are the error estimate of each of the classifier. Okay, so we will look into this. So basically, we for each of the model, we want to compute the weightage of the error. So we will look into that. Okay, so this is the pseudocode for the AdaBoost algorithm. Okay, so basically what we want to do is um, we want to have a few model that will be arranged in sequence order. Okay, so in this case we have up to m model. So one to m model. So we will have the initial weightage will be 1 over nt, which is the nt referring to number of uh, training set size. Okay? So this is number of data that you have. And then the m here referring to the number of iteration, how many model you want to go through, 3 or 4 model. Okay, so if your model is 3, that means your classifier will be arranged like this. C, classifier 1, classifier 2, and classifier 3. And you have the initial data here feed into this classifier. So the result here, the incorrectly classified, so incorrectly classified will have to increase the weightage. The correctly classified will be lower the weightage. So you will repeat this one until here. So this is the formula that we have. Okay. So so when we perform the classification in the first classifier, so we want to find the estimate weightage error. So meaning that we will see all the incorrectly classified, and then we add up the weightage. Okay, and then here we look at the classifier weight. Okay, this is the weightage of the error. Okay, so how do we compute this? We get the 1 over 2 times log of 1 minus error. Okay, this is the total error that we have divided by the total number of error. So for all the correctly classified example, we will reduce the weightage by calculating this one by multiplying the exponent of that total number of error, and then the incorrectly classified example, we will increase the weightage. And then after we update the weightage, then we normalize the weight so that they sum up to 1. Okay, so we will go over these steps, okay, by visualizing the data. Okay, okay. So everyone okay? Can you type number 2 if you're still there? If you're still with me. Okay, so this is very important because it will be in your final, and it will take longer time than you expect because it require basic understanding. How do you turn the question into this? How do you convert the question in the exam into this diagram? Okay, so we start with 10 data. So we have 10 data here. Okay, and we have 5 positive and 5 negative. Okay, so the weightage will be 1 over 10 lah. Okay, so the weightage will be 1 over 10 here. So that's why you get 0.1, 0.1 here. So all of them will have equal weight in the beginning. Okay, then let's suppose we use one classifier. So the classifier saying that whatever in your left will be positive, and whatever on your left hand side will be negative. Okay, so we notice that these three are not correctly classified. So these are the error that we have. Okay, so um, this is the model. We are saying that okay, if this line separate the positive and negative here, so what is the error? So the error will be 0.3. Okay, so we just add up all this value. Okay, so to find the the weight of the error, so we just take this error and then put in here. So 1 minus 0.3, we get 0.7 and 0.3, and then take the natural log, so the value is this one. So that means for this model, the weightage of the error will be 0.42. Okay, so now I want to adjust the weightage so that this one will become bigger, will have bigger weightage. So I want to have this. So based on the formula that we have, okay, now the correct one will be, okay, we take this 4.2, we replace here, we get this value. So what happened is that for all the correctly classified, I will multiply with 0.66. But then for all the incorrectly classified, I will times with 1.52. Okay, so all of this will be multiplied with 0.6, and this one will be multiplied with 1.52. Then you get this. Okay, so everyone can follow. Can you type 7 if you're okay? Okay, so before we proceed to the next classifier, the next model, we have to normalize this. So how do we normalize this? We add up all this value. Okay, so we add up all this value, and the total is 0.918. Okay, so what happened is that I will take this value 0.152 and I will divide with 0.918. Then I get this value. Okay, so that is the normalization process. We we add up all this value, and the value we get will be 0.918. And then we take that value and we divide with this value, and we get the new weightage here. Okay, so that is the first round. First round up to the normalization stage. Now I'm going to the second stage. Okay, so in the second stage, I start with this, and then let's assume that the second classifier says that whatever uh, data on the right hand side, this is negative, and whatever data on the left hand side will be positive. Okay, so in this case we have three items which is incorrectly classified, so we need to focus on this. Okay, but what is the error? We have these three lah. So we add up three, we get this 0.21. Then we compute the weightage of the error for the second classifier. By computing this, we get 0.65. So this is the weightage error for this classifier. Okay, so what we need to do is we need to update the weightage, but first we need to compute the exponent to the power of minus 0.65, and then the exponent of to the power of 0.65. So we multiply this value with these three, and then the rest of them will be used to update the weightage and all of this lah. Then we get this value lah. So notice that the one which is correctly classified, they will become small, like this, smaller value. Okay, and we have here, we have update the weightage for the incorrectly classified item. So how do we normalize them? So we get all this value here, sum up all the value. Let's say the value is x, and then we will divide each one of these by x. Then we get the new value. Okay, so in this case, the value is 0.829. So 0.829. So we will have this lah. From this, we divide by 0.829. Then we get this. Okay. Sorry. Yeah. So this one is the normalized one. This is after the second round. So we can decide to go to the next level, or we can stop here. If we go to the next level, for example, we have the third classifier here. So the third classifier says that whatever item occur above here will be positive, and this one is negative. So we notice that we have three error, 1, 2, and 3. And the total error is 0.14. Okay, so we compute the weightage of the error will be 0.92. Okay, so if we say we will not going to the next round, so we can stop here because we already have the weightage of the error. So the formula that we will have will something do like this. This is the first classifier, second classifier, and third classifier. And if you combine all these three, so this is the region that state where is the positive area and where is the negative area. Okay. So how do we apply this? How do we apply this in predicting a new item? So for example, we are looking at X here. Okay. So we look at the symbol here. So we just, okay, X1 here, X and X. So what we need to do is, okay, this is my negative value, this is positive, this is negative. So we just plug in the value here, -1, +1, and -1. Then we add up all this. So we look at the sign. If the sign is negative, that means they belong to negative class. Okay. So compared to the y here, y is here, y and y. So this is negative, this is positive, and this is positive. So we just plug in -1, +1, +1. Then we get the sign of positive. Then we say this is positive item. Okay, so X and Y is considered as new item. Okay, so we already have computed the area that belong to positive and negative. Okay, but how do we validate, or how do we clarify that that is positive or negative? We just plug in the number, the sign here. Where is the new item located? Okay, so boosting best classifier a bit complex because they require understanding of which one is incorrectly classified, and then how do you compute the error, and then how do you combine them and normalize them and proceed with the next classifier. Okay, okay. Any question? If you okay, can you type number 2? Ah, number 8 lah, number 8. Okay, so the exercise that we have posted is designed for you to get familiar with the calculation. So if you have any question, you can ask me lah.